Okay, so I've got this microphone now. I just got it, so maybe I'll try using it Wednesday. I don't know how it'll turn out. All right. So here we are. This is week 7, I think. All right. So the topic is state and equality. Okay. I guess there's some interesting interaction between these two ideas. All right. Especially when it comes to mutable state. Okay. So far we've been working, I think, entirely with immutable state. Okay. But we're gonna, of course, if you do programming in a non-functional language, a lot of the time the state is mutable, and maybe even sort of globally shared between components of the software. Okay. And so of course we can't just pretend that mutable state doesn't exist. Okay, so we have to talk about that some. Even though in our programming assignments we're essentially not using mutable state for any of it. That's the plan, but we still need to have a good understanding, of course. All right. And right, so the chapters. I think it was only 22 before, and I added chapter 20 as well because, well, it's rather short. And I figure that we shouldn't skip it. All right, so we should read chapter 20 first. Okay. Right. Now I have a little bit to say about this, and then there's chapter 22, which is the longer chapter. It's kind of the bulk of the reading for this week. Okay. Where we're talking about mutable state and how that interacts with the notion of equality, and of course, there's more than one notion of equality. So they talk about this family of equality, this little hierarchy. Okay. And, well, I don't know if I want to. Well, let's look at what it says. Can you click on this? They don't have a nice little. It'd be nice if they had like a diagram that showed it. But of course, you can do the reading to see. But there's this thing called identical, okay, which is kind of the strongest form of equality. Okay, it's essentially reference equality. You say two things are identical if they're, pointers to the same location in memory. Okay, which means they literally occupy the same location in memory, and so they're the same thing. Okay, but then there's a slightly weaker notion of equality. That is the double equals sign in Pirate. What it implements something called always equal. Of course, I'm not going to explain everything here because you can do the reading yourself. But it's a weaker notion of equality where it doesn't require them to be literally the same objects in memory as long as their values are the same. Okay. And there's a third one too that is kind of interesting, I suppose. But that's all I want to say about that, I guess. I do want to talk about mutable references, okay? Because that's really, references are essentially pointers, all right? But the key thing that leads to issues with references is the fact that if you have a reference to something, you can change it, right? That they're mutable references, and that's what makes them interesting. It's what leads to problems. So we're going to look at an example of that, okay? But before that, I suppose I should talk about PA3 a little bit. Okay, so we have a new programming assignment that's due this weekend, and it's up now. It's about binary search trees, and there's a bit about streams. Okay, so we can take a look at the file just so I can maybe explain a couple things. So right away, I give you this eq function, and I highly recommend when you're programming to use this eq function instead of the naked equality operator, because that operator is not type safe. And when I was doing this assignment, I made some mistakes with that equality operator, and if I had used this eq function, it would have pointed them out to me. Okay, so it will probably make your life easier if you use that. Okay, and then there's some code for the result type that we looked at. Well, we looked at option, right? And so this is just like the option type that we saw, except it's specialized to string here. Okay, so normally you would have some type parameter E for the error type. And I'm just saying, well, let's just make it string for now. Okay, and then there's some stuff here for working with it. In particular, we have the seek function, for sequential composition, and it's written a little bit differently, but it's the same thing that we saw before. Okay, it does the same thing, and you've got parallel composition as well, and we have this lift2 function that can lift a function of 2 arguments into the result type. Okay, and we also have lift1. If you remember, there's a lift1 that lifts a function of a single argument into the result type, and but I'm calling it fmap here. Okay, but if you look closely, that's what this is doing, except it's not curried. So instead of taking f and giving you a function from result A to result B, it takes f and the result A and gives you result B. It's the same thing, but it's not curried. You know, it's an uncurried form. Okay, and so this might look kind of familiar to you, actually. And there's a reason it has the word map in the name, is because we've seen something like this already for a different type, which is the list type. If you remember, map for lists is essentially the same thing, just for a list instead of a result. Okay? Okay, and so, even map on lists, well, if you curried it, then what you would have is something like this. Okay, where this is actually lift1. You're lifting a function to the list type. It's the same idea, right? So, this idea of like mapping a function over a data structure is really general. It's not just for lists, but we can use it for results. You can use it for trees. You can use it for just about anything. Any of these, a type that has a type parameter like that. Okay. Anyway. Right, so that's the result type stuff. So that's just some like helper code so that later on when you use the result type, that will be available to you. Okay? And then there's the actual material, the actual work. There's some stuff about binary search trees. Shouldn't be too hard. And then there's some about red-black trees. Okay, so these are balanced binary search trees. And you have to implement this RBT_INF function that is supposed to, it looks at a tree. So here it is. It will look at a tree and return true if it satisfies the red-black tree invariant, which implies that it's balanced. Okay, so this is what you'll be implementing, and it explains here, what the invariant should have in it. And so what I would recommend is to essentially just write a function for each one of these properties, and then make the final one the conjunction of all of them. Okay, and some of these are very easy. Okay, but number 4 is probably the hardest. That you might have to get a little creative. All right. Okay, and then there's some stuff with streams, and so I took inspiration here from the book where it was doing this derivative stuff with streams, and I think I never went over that in class, and so we could take a look at that really quickly. So essentially, what they do is they use this. If you remember the definition of a derivative at a point, okay? So if you have some function f that's differentiable at a, then you can define the derivative of f at a as this. The limit as h goes to 0 of this thing, where you're kind of just, like nudging a little bit and subtracting it and then dividing by h, okay? So this is the definition of a derivative, right? So I would write it like something like, I'll just rewrite this. You take the limit as epsilon goes to 0 of f at a plus epsilon minus f at a over epsilon. Okay? And so a similar way to write this, and essentially what they do in the book is they come up with a stream that converges. So let me say this is equivalent to the limit as n goes to infinity of f at a plus, they set it up like this, 1 over 10 to the n. Oops. Okay, divide by 1 over 10 to the n. Okay, so this is a sequence that as you increase n, this 1 over 10 to the n gets smaller and smaller. So that's like epsilon going to 0. And so what they do is they set up a stream where the nth element of the stream is equal to this for that choice of n. So it's the stream that's converging to the derivative of the given function at the given point. That's what they do in the book. Okay, so what we're doing here is something kind of similar, except we're setting up a stream that converges to pi. All right, it's maybe a little less confusing this way. Okay, and so here's just this. We set up a sequence, which is a stream of numbers that just maps over the natural numbers. So it's going to be 0, 1, 2, 3, but it's mapping this over each of them. Okay, and so if you take this sequence and then consider this its partial sums, the sequence of its partial sums, then it converges to pi. All right, and so that's what we're doing. We're defining a stream that converges to pi in the limit and playing around with it a bit. Okay, so it's just kind of fun. It converges very slowly. So actually, we could take a look. I think you can uncomment that line to have it print out the approximations of pi. What's going to happen? Oh, because it's not implemented. Oops. All right, so we can't do that yet. You have to actually implement this function before you can do that. All right, so anyway. All right, and then there is, for the last thing, just updating our evaluator from last time to use the result type. Okay, so that should be pretty straightforward if you just kind of go by what we discussed the last time using the option type. Okay, and that's it. So it shouldn't be too bad. Okay. Right. I guess there's like one more thing about chapter 22. I don't really have to say this, I guess, but they make this distinction between identifiers and variables, and I don't really like it, but whatever. Because they say, well, they're saying a variable is something that can be changed. It's a mutable variable, right? So they want to draw this distinction where they say identifiers stand for like immutable variables, and a variable is a mutable variable because it can vary throughout execution. But it's kind of a funny distinction to make because, like in math, like they even say here that you use the term variable just to refer to function parameters because it varies across invocations. So it's still a variable in a sense, even if it's immutable within the body of the function. So this is kind of a goofy naming thing, but that's okay. Okay. Right, so now we can get to references. So, yeah. So even though we've only been using, functional, kind of pure functional style in Pirate, Pirate does support mutable variables like this. So if you use the var keyword, then, like when you declare a variable, then later on you can use this update operator to change its value. Okay. And they also have this ref thing. So let's take a look. I'll start a new file. And let's see, where they introduce box? Here we go. This. Let's look at a box and give it a type. Okay, so this is a type here with just one constructor, so we can write it like this. And what it has inside is a reference to a value of type A. Okay? So let's see if this compiles. If it type checks. Oops. Okay. So far, so good. And so now, let's see if I can remember the syntax. How do they do it? So you can read from this. So this is kind of a weird thing. I don't know. We're not going to be using it a whole lot, but we can still take a look. So let's create one, a box, and give it the value 1. Okay. That works. Okay. So the point is, this is kind of like a pointer. This box is like a pointer to a value A somewhere. Okay. So we can dereference the box. I think by doing this. Let's see. Let's print it out. Okay, and it'll print 1 right there. Okay, and so you can also update the box. We can say B1, and then there's this funny syntax for doing it, but it's like this. We use curly braces and then say, well, V should be, some new value. Okay, and now let's print it again, and now it prints a 5 after the 1. Okay, so this is kind of like a mutable box thing that we can use. All right. But now let's take a look at a function, and I'll ask you something about it. I'll call it mutate. Okay. And let's say it takes a box of number and another box of number, and just returns. So I realized, I realized recently that there actually is a unit type. Remember, the unit type is the type with only one element. So in Pirate, because it has tuples, okay, it has sort of arbitrary tuples of like, so pairs are binary tuples. Like this would be a pair of numbers, okay, but you could have 3 or 4. That means you could also have 1. This is a valid tuple type, even though it's kind of pointless to do. You could also have 0, okay? So the nullary tuple type actually is equivalent to the unit type. There's only one element, and it's the one that looks like this. It's the empty tuple, okay? So if we want to return unit, meaning we don't really want to return anything at all, essentially, you can do that, all right? Anyway, so what is this function going to do? Well, let's say we're going to use a block, this is something you use when you're doing this kind of imperative style thing. I'm going to put a sequence of expressions in a block. And what we'll do is we'll say x. Let's update x to have the value 1. Okay, so we're going to update the reference to the value that it points to. Okay, and now I'll update it again immediately afterward to take the value from dereferencing y. Okay, and then we'll just return the empty tuple. Okay, so now you might think that this is kind of a stupid thing to do, and that this function should be equivalent. Essentially, this first assignment is pointless. So this first update, okay, that you should be able to do this instead, and it would be the same thing, right? That these would be equivalent. Yeah, question?
Sorry, what's the exclamation mark symbol for?
So that's for dereferencing the ref. So if we say like y bang v, it's saying, well, dereference v in y because y is a box. And so just like get the value that it points to.
Oh, okay.
And here, if there is a curly brace afterward, that means we're doing an update. So we're actually writing to the reference instead of reading. Okay. So, well, it's an interesting question. I mean, are these the same? Will these always do the same thing when you run them? Does anyone know? Yeah?
Would there be problems if you already have something in it with the second one?
Well, I don't think so. I mean, yeah, it doesn't. It'll just overwrite the old one. I can move this. So that's not the issue. So the issue here is that, well, what happens if x and y both point to the same thing? Okay, we'd say then that that's called an alias. What if x and y are aliases for the same memory cell? Okay, then what happens? Well, then you'd be writing 1 to that memory cell, okay, and then reading it back. Because if you're writing to x, you're actually writing to y also, if they're aliases. Okay, so in that case, you'd be writing 1 to x, always. Whereas here, you would just it'd be a no-op, right? If x and y point to the same cell, then you're just reading from it and writing it back. And so there's actually a difference between these two functions whenever x and y are aliases for the same cell. However, if they're different, if they point to different memory cells, then these will do the same thing, right? And so that's why references like this can be pretty confusing and hard to reason about. It's because of aliasing. Okay, like, well, what if two different references are actually pointing to the same place? Okay, so I hope that whoever teaches 4100 next continues to use Rust, because Rust has kind of a fancy type system for dealing with this kind of issue, aliasing issues. So that's the real learning curve of getting started with Rust is figuring out how to deal with the whole idea of like ownership and borrowing. Okay, you have to work around the type system because it's designed specifically to alleviate this kind of problem. Like, you couldn't write this function in Rust. This is a problematic function, and it would prevent you from doing that. So, I hope that you get to work with Rust in 4100. Okay. Right. Okay, and there's more weird stuff that can happen when you have references. So we've been writing recursive functions all the time, right? Let's write one down like list length, if you remember, and we'll just specialize it to number for now. So you've got a list of numbers, and you want to get the length, and this should be trivial for us now. We don't actually care about that. 1 plus list length r. What did I do wrong? Line 31. Okay, and so this works because Pirate allows us, when you say fun, then it says, okay, the thing that we're currently defining is allowed to appear here, and like the type checker won't complain. All right. Whereas if you tried to write this differently, suppose we wanted to write it as a lambda. You want to say, well, list length should have type list number arrow number, right? And it should be, it'll make a lambda that takes the list and then put the body of the function. Okay. And do this. And so let's see what happens. Okay. And what is this? Oops. Sorry. There we go. What's it saying? Mutate. Did I? Oh, I used the same name. Okay, so now it says, well, the identifier list length at line 40 here is unbound because it's not available there. So you couldn't do this. This list length, if something appears here, it needs to already exist somewhere else. But we're in the process of defining it. Okay, so you could fix this, I think, by using the rect keyword. Let's see if it works. Okay, so then you're telling Pirate, actually the thing that we're defining, I want that to also be available in the body. Okay, so this is a way of doing a recursive definition. Okay, and that's built into Pirate. It kind of has a feature for doing that. But interestingly, even if Pirate didn't provide recursion like this, since Pirate has mutable references, we could actually implement recursion ourselves. So I'll show you a way to do that. Okay, I'll use one of their mutable variables. Okay, I'll say var, and I could call it anything. Maybe I'll call it dummy. And we'll say it should be a list, okay, of this type. And for now, I'll just give it kind of a dummy value that maybe takes the list argument and returns 0. Okay, so it's it's not really the function that we're looking for. Okay, and then when I go to define list length, I'll use dummy there for the recursive call. All right, so this will work. Okay, so there's no recursion going on here, right? We don't have to use the rect keyword because dummy already exists whenever we're defining list length. And then afterward, well, we can just kind of backpatch dummy, since it's a mutable variable. I could update it now to point to list length. Okay, so now what we've done is we've sort of tied the knot. We've done the recursion through the reference. Okay, because now whenever list length calls dummy, it's calling itself. All right, so this is a good way to accidentally introduce recursion into your language. And I have a funny story about this because how much time do we have? Okay, so one of the things that's getting really popular recently is blockchain stuff, right? And and on blockchains like Ethereum or whatever, there are special programming languages for writing smart contracts that run on the blockchain. Okay, and so this is a really interesting area from a programming languages perspective because it's kind of a weird computation model. And one of the properties that is appealing, okay, for these programming languages for smart contracts is that you actually kind of don't want them to be Turing complete because you want them to always terminate. Okay, so what does Turing complete mean? Well, it means your language is Turing complete if it's equivalent to Turing machines. That anything a Turing machine can do, your language can do, and vice versa. And it basically boils down to that. Well, you can encode logic in the language, and it can loop forever. Okay, but that looping forever part is really not always what you want. And so for some of these blockchain programming languages, you actually don't want them to be Turing complete. Okay, so that that the programs don't loop forever, right? Well, there's one. I'm not going to say what it is, but one of these projects actually, they have a programming language that's not supposed to be Turing complete, but they have mutable references. And so I actually found a way to encode recursion in their language, and prove that it is Turing complete when they thought it wasn't. So it's kind of a funny story, but yeah. So that's what I mean. It's a good way to accidentally introduce recursion without realizing it. Okay. Yeah. What time is it? Okay. Well, okay, the book also talks about closures. I don't recall where it introduces closures, and if we skipped that, or if that was in functions as data, possibly. But there's some stuff in this chapter about closures. Okay? So I can just tell you briefly what they mean by that. And we will be implementing closures for our language eventually. Okay? So, but a closure is essentially it's something that pops up when your language supports higher order functions. Okay, so it's in particular when you can return a function from another function. So what do they give an example here. I don't know if I have a good example, but here is one that they use. Okay, of course, closures are a thing independent from references, but here's one that involves references. Okay, so the idea here is that we've got this function called makeCounter, and what it does is it creates a reference by boxing 0. So now you've got a box with value 0, and then it returns a function. So here we should write the type of this. What's the return type? It's a function with no argument that produces a number, I believe. What's the problem here? 49. Might need a block, or yeah. Okay. And so it's kind of funny here. So it creates this counter and then returns a function. And what does this function do? Well, it increments the counter by 1 by updating its value to be the old value plus 1, and then returns the new value. Okay. So if we say counter equals makeCounter, that we can do. Whoops. And this counter is now a function. So if you say print counter, it should give us probably 1. Yeah, printed 1. And now if we do print counter again, it should give 2 the next time. Okay, 1 and then 2. And so the key thing, the reason this works, is that all of these calls are actually referring to the same counter, the same box. Okay, and the reason that works is because of a closure being created for this lambda. Okay, so when you're returning this lambda, it's a function. Well, it gets kind of wrapped up with the current environment. Okay, so that the value you get back from calling makeCounter is a function. It's this lambda in addition to the environment that was there whenever the value was created. Okay, so in scope of this function here is this counter variable. Okay, so that's why it kind of the actual runtime object that you're passing around for this function also carries with it the environment of things that were in scope whenever it was created, which for us here is this counter thing. Okay, and yeah, I mean, I guess the use of closures is pretty common in like JavaScript, but so you might be familiar if you're a JavaScript programmer. But we'll be getting more into that stuff later on whenever we're implementing an interpreter for a language with high order functions. Yeah?
So nothing is going into the process that it's returning something?
Yeah, that's right. So it has no argument, and then it produces a function that also takes no argument and returns a number. Okay? And this is the function that it returns. So what we say here is we'll say counter equals makeCounter. So that's like kind of start a new one. And the type here is, function with no argument that returns a number. And so then you can take this counter and just kind of apply it or call it multiple times, and it'll give you a different number every time. And that's because it kind of holds inside of this counter function is not only does it know how to, not only is it some code, but it also carries with it that box, right? And so that's why you get 1 and then 2 and then 3. Okay. And so, they discuss this here in the book in more detail. But I just thought, I think this is our the first time that we've seen this word closure, so wanted to say something about it. Okay. Okay, and then there's some stuff about this sharing thing. Okay. So, yeah, you should do this reading, but I can just point something out. because this is kind of a performance thing in functional programming. Because the way that we think about our functions is that like they're creating copies of data, right? So you never mutate the input; you just create a new copy for the output. And so you may think that that would be really wasteful sometimes, creating a lot of unnecessary copies. Okay, but it turns out that a lot of the time you don't actually have to make copies. That you can use, you can make use of sharing of data structures, and you can do that because the data structures are immutable, right? So when you have immutable data structures, that means that they're not going to change, okay? And so that means that they can be shared. So let me show you an example, okay? Let's write a function that, say, takes a list and an index and a new value for that index, and just like replaces the element at that index with the new value. Okay, so I'll say replace. I'll take a number for the index, a new value, make this polymorphic, and a list. Okay, and it'll give you a new list. Okay. So now we can write this, and I'll just not spend too much time writing it. Let's do cases on L first. If empty goes to empty. Oops. Link fr. Okay, and now we'll say, well, if n equals 0, then we'll go ahead and do the replacement. Link vr, else link recursively replace. Okay, so just a nice little recursive solution for doing that. Okay, so now let's write a test case for it to make sure it works. Let's say replace something like this should be what? List 5, 6. See if that works. So if we replace the element at index 2 with 5 in this list, we should get back that, right? And it works. Okay. Okay. So what's interesting about a function like this, though, is you might think, well, so if it takes the input list, it doesn't change it. It produces a brand new list as the output. That's the way that we think of it, right? And so that means it has to create a copy of the entire thing. But actually, internally, it doesn't quite have to do that, because when you get to here, in particular, when you hit this case, if you see, it's just taking R and tacking on that same element. Okay, and so then essentially what happens here is that it'll get down to that index, and then it'll say, okay, do the replacement, and then instead of creating a copy of the rest, it can actually just reuse the same one. Okay, and so when you think about like the internal memory representation of these two lists, they're different up to this point, and then they actually could use the same memory cell for the rest of the list. And while the rest of the list could have been very large. Okay, and the reason it's safe to do that is because the lists are immutable. So it's safe for two different lists to share some part of their structure whenever that part will never change, right? So then one of them can't change it under, under the nose of the other one. So there's actually kind of a performance benefit to immutability, and it plays nicely with our conception of how functions work. Okay, where you can kind of think of them as having their own copies, because it doesn't matter. It doesn't if they don't actually have to have their own copy, because because the data is immutable. Okay, so all right. All right. So I don't know what else to say today. Let me look at the schedule again. Right. So, I mean, we could get into the weeds with state, but I don't know how far I want to go into that stuff. It's possible that, so when I'm kind of in the process of designing these things. They're going to be a bit different from last year. But I'll probably at the very end have some kind of extra credit, PA7, and what it might be is to extend our programming language to include support for mutable references. Okay, maybe. And so then you have to build in some notion of state into the interpreter that we implement. Okay, so that's a pretty non-trivial extension to the language. But, I don't think I want to include that in the base language. Okay, and so probably instead of like really getting into the weeds with state, probably what we'll start doing soon, maybe even Wednesday, is talking about this material. Okay, abstract syntax and parsing. Okay, we can look at recursive descent parsing, and then my plan though for PA4 is for us to not use a recursive descent parser, but to use a slightly more advanced technique using the result type. Okay, sort of a combinatorial parser. Okay. Right, and then we have a midterm coming up pretty soon. I haven't written that yet, but probably one of the days next week will be like a review day, I suppose, if we have time.
Will the midterm be on in-person or online?
It's a traditional in-person midterm in here, I suppose. Right. So what time is it? I don't have anything else to say today, so we'll probably stop here. Could possibly have a quiz.
So did you send that crypto CEO an email letting him know that his language is wrong?
Well, I'm currently waiting on a response, not from the CEO, but from one of the designers of the language. So
What was it? What crypto was it?
I don't know if I should say.
Why not?
I don't know. I guess I could. It's called Kadena. Okay, Kadena. It's kind of a smaller project, but it's growing. Okay, they use Haskell. Okay, that's why I'm interested in that. Okay, let's see if we have a quiz.
I think Cardano also thinks that Haskell is turning complete.
So Haskell is turning complete. But so this other project, though, they use Haskell to implement a lot of their stuff, but the programming language for smart contracts is not Haskell. It's something else. Okay. Let's see. Okay.